Okay, good morning everyone. Today we want to look at a variant of the derivation of the Einstein field equations. This is a continuation sort of from the last presentation that we've had. I think that should be basics 1C. Because here we'll also be talking about the energy momentum tensor, and we shall be making comparisons with the derivations we made in that lecture. So at this point in time, we want to look at the variational principle. First, we have to define the action. And for the derivation of the Einstein field equations, the action is defined to be that due to the gravitational fields plus that due to other fields. And so we also have the Lagrangian for the gravitational fields and that due to the other fields. And our covariant measure here multiplied with the square root of minus g. We shall be in this case defining the Lagrangian due to the gravitational fields as that c raised to the power 4 the speed of light all over 16 pi g, the Einstein gravitational constant, multiplied by the Ricci scalar, which is denoted there by capital letter R. So in other words, in calculating this variation, of course by variational principle, the variation of this is equal to that, the variation of that plus variation of this, and that should give us 0. That's the method by which we are going to proceed here. Here, of course, we're just going to perform the variation naively. We're not going to state ab initio what the variable for this variation will be, but it turns out we're going to see, of course, what it will turn out to be and how this will be important in the derivation of the energy momentum tensor, which is something we shall be doing also towards the end of this lecture. Looking at this expression, and like we stated, of course, from here, when you expand this expression, especially after you substituted this expression or this factor here for L sub g in this expression, and then you just open the bracket a bit, you have these two integrals. So I'm going to call, of course, this we have named, so maybe I should start somewhere here. The variation of I sub g is the same thing as c cubed all over 16 pi g integral of the variation of r square root of minus g before x. Note that this is not equal to 0, remember, because what we said is equal to 0 is the variation of this overall action. So this individually, their variations individually is not equal to 0, rather is the variation of their total sum that is equal to 0. So whatever we do here in the end, we will not equate the resulting integral to 0. So at this point then, we'll have to calculate this, then keep whatever result we get, and then proceed to get the second one. Okay. The Ricci scalar, by the way, will be obtained by any of these contractions, mu nu, for instance, r sub mu nu, or we could say this is mu nu, r mu nu. For the purpose of this derivation, I'll be using this variant because it's most preferable, or well, we'll just see that it falls naturally with other variations we shall be obtaining, and especially also with the Einstein field equation we shall be deriving. So at this point in time, we have that to be what is obtainable. So what we are interested in is the variation of this factor, so that the variation of this minus g is the same thing as the variation of some g mu nu r mu nu square root of minus g. And for convenience, or well, maybe I can say that this is the same thing as, let me get the same thing as saying the variation of r mu nu g mu nu square root of minus g. So at this point, I could say that this is something as the variation of, okay, so I'll have to erase that. So let me put it this way. R mu nu, first variation of g mu nu square root of minus g plus g mu nu square root of minus g variation of r mu nu. Well, note that I could have as well split the variation here. I just choose to do it this way so that I could handle this separately. It's more convenient for me that way. So let's look at the variation of the Ricci tensor. So we had the Ricci scalar to be defined as the contraction of the metric tensor and the Ricci tensor. That gives us the Ricci scalar. So looking at the expression here that we have for the Ricci tensor, which is given by that, The variation of the Ricci tensor, looking at this expression here as we've written it out already, this is the same thing as the variation of gamma alpha mu nu, comma, alpha minus okay, so based on what we have here from the expression, we take variation of every factor, even for the terms that we have two Christoffel symbols multiplying themselves. We just take the variations of each factor, so we vary this, keep this constant, plus we keep this constant, vary the next one. Minus the one here with two Christoffel symbols. You can see, so the same thing, we are going to vary this and keep this constant, plus we keep this constant, we vary that. And this is what we get. Okay, so there are two ways to go about this. Well, let me just go by which I think. So first of all, I could decide to perform the covariant derivative of the variation of this. For instance, the covariant derivative of the variation of this Christoffel symbol. And now this is what we've got. The covariant derivative with respect to x alpha. This will give me, for instance, just the partial derivative with respect to s alpha plus, I have a Christoffel symbol, I intend to contract alpha, I use delta, but then again I'm differentiating with respect to L with s alpha. What I'm contracting is alpha, so I bring alpha over here. And now I'm going to have the variation here, delta, with that which I'm contracting, I have mu nu. So I've contracted the first index on top. Minus, contracting the lower index, or one of the lower indices, I have here delta, and then of course the variation, and so one of those indices is mu, so that will be replaced with delta, mu stays here, and alpha comes over. And then the one that I'm not contracting is nu and alpha. Then minus another contraction of the lower index, and what I'm contracting this time is nu, so mu stays as it is, alpha also, but nu comes over here, and then I should get an alpha too. So I have here for three indices contracted. Following this particular expression also, I could perform a contraction or the covariant derivative of this is alpha. I have to be careful with these indices before we run into very serious lengthy algebra. Okay, so this is what we have here, that is alpha. So at this point again, I just go ahead and do the normal thing, differentiate ordinarily with respect to x nu, then plus the Christoffel symbol, and now I am supposed to get a delta. Okay, the delta will have to be down. I'm differentiating with respect to nu here, that is nu. This is variation of some delta. What I contracted was alpha, so it comes over here. And then of course here stays mu and alpha the way they were, nothing happens to them, because what we've just done so far was to contract what is on top. Now the next thing I do is to minus, I subtract here a contraction also between a contraction of, okay, so I just contracted the upper indices, one of the upper indices, or the upper index here. I will be contracting mu, so I will write here delta, and then the variation, alpha is left all alone, mu has been replaced by delta, it comes over here, and then nu joins here because I'm differentiating with respect to nu. And then alpha, of course, that is here remains as it is, nothing changes. And the last index I'll be contracting is alpha on that, so, and that will be contracted using delta. And the variation of gamma, I have here with me mu, I have here with me mu, and this mu here, of course, is untouched, so I am contracting alpha like I've said, so delta replaces alpha, so I have alpha here and nu following, and of course the other alpha that is on top here is untouched, so we leave it as that. Okay, now looking at some of these expressions, we could do something especially maybe about the second one. We have here alpha nu, nu delta. I have here also delta but alpha nu. I have alpha, mu, delta. So kind of looks like if I interchange delta and alpha in this expression, such that what I've got here will be alpha and this will be delta, right? And you can see that that will give me the same thing as what I have on this particular Christoffel symbol. And then here also will be delta. This will be mu, but then the delta here becomes alpha, and then again this is the same as that. And of course the two are the same except for the signs. So straightforward, I just cancel them out. So in other words, this expression should be the same thing as that. Alpha mu, alpha comma nu, but minus what I've got here is delta mu nu, and that here alpha delta alpha. Now you can take note that there is no transformation whatsoever that I can perform here that leads to any further cancellations on these separate expressions. We were fortunate in making that here, but that you can see obviously is not the same. I have alpha alpha, so it's a dummy index on one Christoffel symbol. No, there's no such thing occurring here. Okay, now what I am going to do straightforward is I want to make this subject of the formula. In other words, I can write that this alpha mu nu comma alpha is equal to the variation of alpha mu nu alpha minus alpha delta alpha delta mu nu. Okay, so now plus this will become delta mu alpha delta gamma alpha delta nu, and then plus delta nu alpha delta gamma alpha mu delta. That is that. And then of course this last one here, well, let's just sandwich that somewhere here. It means also that alpha mu alpha comma nu is the same thing as the variation here of alpha mu alpha semicolon nu, but then plus of this mu nu, and then I have the variation of alpha delta alpha. Okay, now I have to be careful with that. I'll make that longer. So this should be delta alpha, and I have alpha with me here. Okay, so the intention here is I have this to be in commas, so I want to substitute them here and here. Of course, I already know where I'm going. I just want to see what plays out or what I get in the end, especially since I'll be getting them in terms of covariant derivatives or their variations. So far at this point, I would like to take this one step at a time. So let me just erase these next two lines on top and see what we obtain from there. So it therefore means that the variation of r sub mu nu is the same thing. So in place of this, I'm going to write out all the expressions responsible, or all the expressions that could be used to replace that. This is mu nu comma alpha, mu nu comma alpha, minus gamma alpha delta alpha, variation of gamma delta mu nu, and then plus gamma delta mu alpha, and then I have next variation of alpha delta nu, and then I have next plus gamma delta nu alpha, and I have variation of mu delta here and alpha. And that is the first term following this expression. That is the first term here. So all I've done is to have substituted. So you can look at the method again. First of all, I have these first two terms. I try to kind of write them rather in terms of covariant derivatives and not partial derivatives. So I sort of perform the covariant derivative of this variable of variation with respect to x alpha, then write this in terms of that. So I simply made the subject of the formula, and that's what I've just put here. So everything I've written so far is simply replaced by, is just represented by that. So in other words, I still have this to go with. So next I'm going to say minus. And minusing, again, what will be representing this will be these two terms here that I have below. So I'm going to have here minus the variation of alpha mu nu, and I guess that is covariant derivative with respect to, oh no, that is mu alpha. That is mu alpha, covariant derivative with respect to x nu, and then minus again, gamma here, I have the delta mu nu, and then it has to be the variation of alpha, delta alpha. So in other words, all I've done so far is to have written out these first two terms, and that is what I've got there. So the next thing I'm going to do is just again write out these terms, what they will be. So I have written this minus that. So next I have plus variation of gamma alpha mu nu, gamma beta alpha beta, and then plus alpha mu nu, variation of gamma beta alpha beta, minus variation of alpha mu beta gamma beta nu alpha, and then finally minus alpha mu beta variation here of beta nu alpha. Okay, let's see what this gives us. Right here now we are simply going to, oh no, I suspected that might happen. Please, you can take a very close look at this particular term here. And this term here is saying, as you can see, this was actually a covariant derivative. And I just noticed that I didn't denote that here. So all I did was to use a partial again. I didn't expect that. Like I said, it was pertinent for me that I wrote them in terms of covariant derivative. So this was originally a covariant derivative, and that's what it should be. So now at this point, I'm going to see or look for any possible cancellations. So the whole thing here should be equal to, let's see first of all, this is alpha, alpha, delta. First, let's see, is there any such Christoffel symbol with dummy indices on one of them? Looking at this, okay, well, on this one here, I have beta, beta, alpha. Okay. And then, of course, one of the dummy indices, the delta is repeated here. So take note of this. This is a variation here of gamma, alpha, mu nu. This is a variation of gamma, delta, mu nu. So without being redundant, just take note here that I could decide, or I could change beta here. Okay, well, maybe I can interchange, or simply put, I can change alpha here to become delta. And if I did, I can do that because they are done in this. So let me just do that straight ahead. So this becomes delta, and then change the betas to alphas. If I did that, this will just be the same with that, and then again except for the signs, and so the two of them cancel. Again, looking at this, I have some delta mu nu, so we just have to look. Is there anything with such thing as delta mu nu? No, I have here delta nu alpha. Besides, they're the same sign. I don't think there's any need trying to. There's of no point. I have to look for something with an opposite sign with the hope that I will get some cancellation. Okay, so here I have, okay, so maybe I will look at this one. Here I have alpha mu beta. Okay, well, we have here the betas, just like here I have alpha, alpha is a dummy index, I have beta, beta. So because of that, I can change it to alpha if I wanted. But then again, I have another alpha here, so that wouldn't be wise because I will have now 3 indices on just one term. And if I want to be straightforward and clean with this, I should have the maximum of just 2 indices on every term. Oh, but well, I can decide to work on this one instead. So since I have here mu beta, I can change the alpha here to beta. And if I did, this becomes beta just like it is here. So I'm going to change that to beta. And then the alphas here, the alpha here, so the deltas here I'm going to change to alpha. Again, I can do that because they are dummy indices. So this becomes alpha, this beta, and that beta. And then again, of course, because they are just the same and of opposite signs, they cancel. Well, maybe I should say nu alpha nu doesn't matter on the Christoffel symbol because it's symmetric with respect to the lower indices. So these are just exactly the same and they cancel out. Okay, now looking at something again with opposite signs, I don't know whether this, so I have here beta nu alpha. It doesn't look like this, so I better look at this one for instance. Oh no, this has a minus sign and a minus sign. Okay, so maybe I can look at this term here. So I have a minus here, but okay, the Christoffel symbol here that is not varied, has beta nu alpha. So I have here delta nu alpha. I'm guessing that if I just change the deltas here to betas, which I can do because they are dummy indices, I'm guessing this will look just the same as that, because if I change the deltas here to beta, then I'll have a variation of the gamma alpha mu beta, which is the same thing here, the variation of gamma alpha mu beta. And then I'll end up with some here, gamma beta nu alpha, which is just the same thing. So these two again cancel. Okay, now we're left with two more, which we hope and expect really that they cancel. So this is alpha mu nu, but this is delta mu nu. And here, instead of alpha alpha, I have beta beta. So I'm guessing it's all just the same. Okay, first of all, I can interchange beta here with alpha. In other words, wherever I see beta, I put alpha, and wherever I see alpha, I put beta. Note that it wouldn't change anything on the lower indices for this object. If you see, because in the end, what it means, I will change this to beta and then change this to alpha. But then again, the Christopher symbol is symmetric with respect to the lower indices. And so when I add beta alpha or alpha beta, it doesn't matter. So this, by the way, remains the same. However, I will necessarily have to change this to alpha if I perform that interchange. This becomes alpha. Okay, and of course the alpha over there, remember we're making the interchange between beta and alpha. The alpha over there has to be beta. So this becomes beta. Yeah, that's what I get. Moment. So it becomes beta. Now you can see at this point what I've got is alpha. Well, so what I want to do right now is quite simple. I have deltas here. So the betas here are dummy indices again. Because it's a dummy index, I can decide again to change the beta to delta. So, and if I change the beta to delta, so the next transformation on this same term is changing beta to delta. And if I did that, it will be exactly the same with this term. Again then, except for their signs, which allows us to cancel them. So quite quickly, very simply, we have this mu nu minus variation of, so the only terms that I haven't cancelled are these two. And this is one way to obtain the variation of the Ricci tensor, as we have shown it here. We haven't made any assumptions, we simply just made some substitutions and wrote partial derivatives here in terms of covariant derivatives, as you have seen, as we've just done a few moments ago. Now, one other way to obtain this is to simply say, okay, well, and writing this out, we choose a geodesic coordinate system in which the Christopher symbols all vanish except their first derivatives. So the Christopher symbol all vanish, but any Christopher symbol that is differentiated with respect to S mu alpha or any of those wouldn't be zero. In other words, these two will have to be zero because it has a Christopher symbol. This term too will be zero because it has a Christopher symbol. This term too will be zero because it has a Christopher symbol. And this too will be zero because it has a Christopher symbol. So in the end, this will give me this alpha mu nu comma alpha minus gamma alpha mu alpha comma nu. Okay, well, but then you can see that it's not covariant, the same as covariant derivatives here. So what do we make out of this? Well, the thing here is I can also just decide, as you have seen me do already. Oh no, I just erased the expressions. Well, to calculate, I could rewrite this all as this alpha mu nu semicolon alpha minus that alpha mu nu comma nu semicolon nu. I could write this as this with my assumption still that the Christopher symbols vanish for a geodesic coordinate system. Now, if the Christopher symbols vanish, now just take note that by the time I write out the covariant derivative of this variation, what I'm going to get is the first one, the object itself differentiated partially with respect to S alpha, which will be that. Then I'm going to have plus a contraction of this and minus contraction of this and minus contraction of that. And each of these contractions have a Christopher symbol multiplying them. So if the Christopher symbol vanishes, it means these other terms also vanish. Right? Of course, the same thing is applicable here. So that in the end, by either by that assumption, you have that this is given to you to be equal to that, or that this is also just equal to that. So we have just shown you this by two methods or by two ways here. And that's that about the variation of the R. So I guess I'll just leave that on top. So the next thing that will be of interest to us will be to calculate the variation of this. We've just obtained the variation of that. Okay. Very quickly, that is the result. So maybe I think I'll write it all on top here to make for a cleaner set of expressions. So this is the same thing as alpha mu nu alpha minus, here gives me, oh no, that is quite unfortunate. Well, but I believe it's just the same thing. It's just me having to copy this. It is alpha mu alpha, and that should give me nu. Okay, so working by our second method, I believe that should be our expression for the variation of the Ricci tensor. Okay. Now the next thing is to calculate the variation of the object here in the bracket, which is this. So the variation of g mu nu square root of minus g. This is the same thing as some square root of minus g variation of g mu nu, and then plus g mu nu variation of square root of here minus g. And of course, the variation of square root of minus g is the same thing as some square root of minus g, the g, and then we are going to have here with us, this should come up with the following, the variation of g itself. Exactly what it will be expected to be, and then okay, well, so the variation of this, first of all, I don't think this will be necessary. We've done this already, one of our lectures, and by the way, I've written out the expression. This was our very first lecture on the basics of general theory of relativity. We obtained this, you can just confirm that by looking at that lecture. So very simply, instead of having to make this too cumbersome, I'll simply put that the variation of the square root of minus g, so here all over again is minus 1 over 2, square root of minus g, g is alpha beta, and then here g alpha beta. Okay, so all I have to do is to substitute that here. And then this, of course, I'll have to find a way to make that work. So therefore, g mu nu is the square root of minus g equal to square root of minus g, variation of g mu nu, then minus 1 over 2 square root of minus g, and then I have g mu nu, gs of alpha beta, and variation of g alpha beta. That's what I get. Okay, now the only thing I'm going to do next is to simply look at this as, okay, so maybe the first one here, or should I say, yeah, this one here. So I'm going to write this here as g mu nu square root of minus g times the variation of the Ricci tensor. Now this, of course, is just the same thing as having the square root of minus g. Maybe I can have that outside. And then I have here g mu nu, variation of gamma alpha, that's just writing that in here, minus another g mu nu, variation of here alpha mu, alpha, and then nu. Okay. The next thing then it means is for me to write what r mu nu here multiplied by the variation of g mu nu square root of minus g. This should give me, okay, I think I should work something out here first because I'm going to have to make some simplifications. And so the first thing I'll do is say r mu nu multiplied by the variation of g mu nu square root of minus g. This should be the same as square root of minus g r mu nu variation here of g mu nu minus 1 all over 2 square root of minus g r mu nu, and then I have here with me g mu nu and g alpha beta variation of g alpha beta. Okay. Looking at this expression here, I have almost like a common factor here. I have here some variation of G mu nu, but then I have the variation of G alpha beta here. So I would like to make the change, and note also that here in the variation, so you may actually fall to this trap. It's a common mistake, but you should watch out. I have already the expression written as a variation of G mu nu multiplied by the square root of minus G, which again is in terms of some square root of minus G and the variation of G mu nu. Now I wanted to substitute another object, which is the variation of the square root of minus G, into this expression, and which will be comprising of dummy indices. It will be wrong for me to ab initio call this mu nu. Again, because according to our laws in tensor analysis, you can only introduce a new index that is not already present in the expression. So which was why I used alpha, beta, rho, sigma, anything else, iota, kappa, and the rest of it can go. That is the only way you can do this. Otherwise, you will end up with the erroneous solution that so for the sake of convenience, just to make the G mu nu here, variation with respect to G mu nu the same with this one, you now say, okay, this is mu nu, and then go ahead to substitute. It will be wrong, and like I've said severally, of course, if I had done that, I will have mu nu here and mu nu here instead of alpha, beta, and alpha, beta. And that will make the dummy indices more than 2 in one single term, because this is mu nu, two dummy indices occurring twice, and that's enough. You can't have another mu nu all over again on the same expression. Okay, having said that, how then do I make some variation of G mu nu out of this expression? Quite simply, I can say let alpha be interchanged with mu, and let beta also be interchanged with nu. And again, this is an expression, or this is an operation we can perform because we are talking about dummy indices. Were this not to be dummy indices, we can't do that. Now, so having said that, I have this with square root of minus G, R mu nu, variation of G mu nu, minus 1 over 2, the square root of minus G. Now, I said I was interchanging mu with alpha. So wherever I see mu, I put alpha. Wherever I see alpha, I put mu. So this should be alpha, and the nu there should be beta. And then G here should be alpha, beta. But then the alpha here should be mu, and the beta should be nu. So variation here of G, mu, and also nu. So that's the essence of this operation. Now, if we did that, you can see now I have variation of G mu nu here and variation of G mu nu. Something else is common, and that which is common is the fact that we have a square root of minus G, which is on both sides. So, well, let me try to, okay. First of all, I can say, and take note also that this combined together gives us a contraction of just the Ricci scalar, R, without any index on it. So what I've got so far is here R mu nu, but then minus 1 over 2 and R over there multiplied by some G mu nu, and then the brackets here. Now you can take note of the fact that, like I've said, we have here with us some common factors of square root of minus G and also the variation of G mu nu. Now you can take another look at this again just to be sure you understand. The square root of minus G multiplied by this and then that minus that. So I've picked out this and this to be what is common, so I'm left with just this on the first one. And then minus, again, I'm going to pick out this and that. So I'm left with 1 over 2, but then the combination of this I said is R, and then G sub mu nu, and that is what you've got. Yes, so that is right. So at this point in time, all I can do is simply to substitute in place of this and that what we have obtained so far. We've already obtained this, which is this here, and that is that. And also we have obtained this first one, which is what I've written as that. Okay, moving forward, we proceed as follows. And this is, the whole thing is equal to the first one here, which is what we've got here. This is R mu nu minus 1 over 2 R G mu nu times the square root of minus G, variation of G mu nu, And the next thing is going to be plus, what have I got here? This is plus the variation of this which we already have here. This is again the square root of minus g mu nu, here variation of t, say t gamma, mu nu, covariant derivative alpha, minus g here, mu nu, variation of alpha, mu alpha, covariant derivative x mu. Okay, we still can go on manipulating. For the sake of convenience, I'll simply identify this as the esteem tensor, and so label them accordingly. This is g sub mu nu, and then I have here with me square root of minus g mu nu. Here plus, I'm going to have the square root of minus g. Take note of this. The fact that the covariant derivative of a metric tensor is always 0. Yeah, so we know that g mu nu, covariant derivative with respect to alpha, or g mu nu with respect to anything at all, this is always 0. The fact that that is the case means that I could write the second expression as g mu nu, variation of here, alpha mu nu minus. Okay, I think what will be most important for me, I will do that, but in a moment. The first thing I would like to do is to make some interchange so that I can have a common index here to pull out. And that isn't a difficult thing if I make an interchange between nu and alpha on this term. In other words, nu interchange with alpha. So for the next term, I will have here still g mu nu, and have here alpha mu nu. I have here alpha minus. Again, I can do this because nu and alpha are dummy indices. So this is mu, but then it's going to be alpha here. Variation of, instead of alpha, I have nu over there. Mu, nu here, but then I get alpha. I guess that is that, and that is what we've got. So I have here a common index with respect to which we're differentiating covariantly. And so this is the same thing here as g mu nu, square root of minus g, variation of g mu nu, and then I have here with me plus square root of minus g. And what I intended to do the other time was to bring all this together in a bracket, minus g mu alpha, nu mu nu, and then this will be covariantly differentiated with respect to x alpha. Of course, so that by Leibniz rule, what I will be forced to do here is to covariantly differentiate this first and keep that a constant plus. Keep this a constant, differentiate that. For the first time, it will be 0 again, because like we've said, the covariant derivative of the metric tensors are 0. Okay, well, we can make an identification of this object here in the bracket. Mu mu are contracted, nu nu are contracted. Mu mu contracted, nu nu is contracted. We have one covariant index on top. We can refer to this term, just label it P alpha with the covariant index there. And so this gives us g mu nu, square root of minus g, variation of g mu nu. And so I have here would be plus the square root of minus g P alpha, covariantly differentiated with respect to x alpha. Now, one of the expressions or results we have obtained, I believe, if not in the first lecture, maybe second or third, but I'm sure we've done this. And it comes from this relation here. So you can see this to recall that we have shown especially that for any vector, covariantly differentiated, or maybe the four divergence, covariant four divergence of any vector, you can see the alphas contracted. It could be written as that 1 over square root of minus g dx alpha, and then times acting on that. And of course, it's the same if we were talking about some, let's say, an antisymmetric tensor, C beta, and I was doing something like either alpha here or beta, okay, let me say beta or whatever. But if I am covariantly differentiating that, and that was an antisymmetric tensor, you obtain something like that too. So in other words, quoting that from this result, you can see that dx alpha is the same thing as this object comma alpha, just like I have it here. So if you multiply across with the square root of minus g, this is what you get. So take a good look at this expression, because I'm about to make use of it. And so having this, it means I can rewrite this second term here as the square root of minus g p alpha But then what will be outside will be simply comma, not semicolon. It changes from semicolon to comma. So, and this all is equal to G mu nu, square root of minus G, variation of G mu nu. I think I might have been missing. No, I'm missing nothing. I think so. Well, you can see everything we have done so far has been possible, and we have done it all outside the integral sign. So very quickly, right now, I think we've obtained all we will need for now. The only thing we'll be careful in trying to remember is the fact that, so maybe I should put that here, is the fact that we have named something G mu nu, which is equal to here, R sub mu nu minus 1 over 2 R G mu nu. That is all we need to remember. But then, of course, if we remember, we started with saying variation of G to be equal to C cubed all over 16 pi G. And now we took the integral with the variation of R, square root of minus G, and then here the 4x. Yeah. And now take a good look at this. That the variation of this, that in other words, what is here is what we have obtained so far to be equal to that. So I could say in the next few steps that this is the same thing. So I will simply keep this out of the bracket, pi g, and do something like this. I call it bracket. So it means I'm going to have instead the integral of g mu nu square root of minus g. Here I have variation of g mu nu, the 4 of x. Then here is going to be plus another integral, but then I've got here to be square root of minus g, p alpha, comma alpha, and then again the 4x. In my next development, I will not need the precise form of what p alpha is. I don't need that, because eventually that will be 0. So I can just move forward and confidently erase that. So moving on, having obtained the expression in that form, we could say, well, that this is also the same thing as c cubed all over 16 pi g, and then I have here with me integral of g mu nu, maybe write it in that form, square root of minus g before x, plus, by Gauss theorem, this could be written as simply the square root of minus g, but p alpha, oh no, well, looks like I needed, but it's no problem. This will be the s. Yeah, that will be the s. So I have here with me by Gauss theorem converting this divergence for divergence into just what we found the divergence, and then the integral is taking over the surface. And if you remember, so I'm sorry I have to say that if you remember, else I should have just shown you that, but I erased it. P alpha was composed of the variations of gammas, I believe, that's what it was, the derivative of gammas. Now, in the assumption here that we are making by the variational principle is that these variations vanish on the boundary or the surface over which we are performing the variation. And that is for the reason, and that is the reason for which this will eventually be 0. Not necessarily because we're integrating over all space. So whether over all space or not, this will be 0 because of the fact that this object, which is P alpha, you can just play this back a little more.